Right, we are live. I'm still opening my audio software. I just realized I forgot to do that. How is your Wednesday going?
Great. Yeah, I mean, normally Wednesday is my day off, but I'm going to make a special occasion for a special case for this. We specifically pushed back the Astronomy Cast recording, although we could have probably done it in retrospect. But
we didn't know how much information was coming.
Yeah.
I was hoping for a lot more information than what we got.
Yes. Yeah. But yeah, so we pushed it back so we could talk about this now. And so let's do that.
All right.
Are you ready?
I will be in just a moment. File, new audio file. This is episode 761. All right. I should make sure it's using the correct hardware. You will be happy to know I brought my condenser mic back downstairs.
Oh, good. Oh, good. I won't have to hear your hair scraping against the microphone.
I'm sorry. All right. I am pressing record. I am pressing record. We are recording.
I am also pressed record. All right. All right, I have an intro here. Okay. Astronomy Cast, episode 761, Vera Rubin. Welcome to Astronomy Cast, our weekly facts-based journey through the... No, actually, we'll do this again. Astronomy Cast, episode 761, the Vera Rubin Observatory. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain. I'm the publisher of Universe Today. With me, as always, is Dr. Pamela Gay, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am deeply regretting checking out social media prior to this recording because today is a day that reminds me it is our next episode where we will contemplate cuts coming to NASA and the National Science Foundation. But
yeah, and the timing should be pretty good because we know a lot more now, so we'll be able to cover it in sort of in all the grim details.
Yeah. There are a lot of people actively crying right now in the astronomical community.
Next week, it will not be a happy episode. No. It will be a sad episode. Yes. Well, the time has come. The mighty Vera Rubin Observatory has finally come online and delivered its first light images. And by Pamela's rules, that means we get to talk about it. So let's do that. And we will talk about it in a second, but it's time for a break. And we're back. All right, Pamela. Wow. What a week.
Yeah. It has been all the highs, all the lows, all the chaos. Yeah. But today we're going to focus on one good thing, which is the stubbiest looking giant telescope on the planet.
Yeah, the largest camera on the planet, the fastest big telescope on the planet. The superlatives go on. Yeah. But it's interesting watching the coverage from the mainstream media about Vera Rubin because they're oohing and awing over the pretty pictures.
Right, but that's not what it's there for.
That's not what it's about. No. And so it was incredible. Like they were great pictures. Like I love some pretty astronomical pictures. But what we hope to convey in this episode is why this is one of the most astronomical instruments that's ever been delivered to scientists, and how this is going to change astronomy. Yeah. So let's where do we want to start? Like, do we want to talk about the observatory? Or do we want to talk about sort of first light? Let's talk about first light first. Okay. So we got the news. I guess the embargo the embargo wrapped up, was released on Sunday night at midnight Eastern Standard Time. For me, that was 9:00. Yeah. And so I could we saw the first pictures. Mm-hmm. And, I'm sure many people in the astronomical community had already seen them. People who follow embargoes had looked at the pictures. I refuse to look at embargoed stories. And so I saw them for the first time like everybody else did when that embargo lifted. Yeah. And so you saw them Sunday night, and then we saw the full press conference Monday morning. So what were we looking at when we saw those pictures? And hopefully, people who are listening to this episode, you remember the pictures, you can bring them out. What are we seeing?
So they released Three significant things. Their SkyView data tool that allows you to take these images. One of the things they kept pointing out is a typical 4K image is 2% of an image that Rubin takes. So you can't just enjoy, no matter how big your monitor is, all of one of these images at the same time on one monitor. So they released a SkyView image explorer that allows you to pan, scroll, zoom, all of those things.
Yep.
And they released two basic images. One that was a field of literally millions of galaxies, which was kind of awesome. And they varied in redshift. So we were seeing everything from relatively nearby objects out to the distant extremes of our universe. They also released an image of the Trifid-Omega Nebula Region. So star-forming region galore, all of the pink pretty details, all of the black Bach globule type stuff floating in front of it. And so we had these two different images, and then they highlighted some of the things in the galaxy image, because the Trifid-Omega image, it's a lot harder to highlight these things in. What they were highlighting is each deep image they showed us was actually a whole series of individual images taken across multiple filters. This telescope has 5 different filters. And as asteroids moved through the field, they were able to identify not 2, not 3, but 2,104.
Yes.
Which is a lot and kind of amazing.
Yeah.
And these objects ranged from near-Earth objects, not putting us in any danger, out to the far edge of the asteroid belt. They couldn't really see much further out into the solar system because they only had 10 hours of exposure, and you start to just not being able to resolve the motion that well. But they also showed us highlights of variable stars. Now, for the variable stars, you have to look in the same filter for each image. So all of us had a bit of a sad moment because we didn't exactly get beautiful images of these variables pulsating in brightness as all of us, especially me and my variable star-loving heart, would desire. Instead, we got, here's an image. Here's several hours later, here's an image. And you could see several tens of % brightness change. This is a machine that is designed to identify everything that flickers, flares, and moves in the night. And they demonstrated on Monday that this telescope is here to do its job.
Yeah. Yeah. And I think what the general public got from this was, look at these pretty pictures. Yeah. It's taking beautiful pictures of galaxies, beautiful pictures of nebulae. But those of you who have been following images from James Webb, images from Hubble, you've seen what the Gemini telescope, Gemini North-South, the DESI survey, the very large telescope, the Keck Observatory, the large binocular. Like, you're familiar with pretty pictures of space.
Yeah.
And so for me, like, they were great. Like, I liked them, but they were not the point.
No.
The point was the conversation about the asteroids, because that was what really sort of sharpened our idea and our understanding. And what that telescope did in 10 hours of observing one tiny little patch of the sky is ludicrous. So on average, astronomers report about 20,000 new asteroids a year. We know of about 1 million asteroids total. A tiny fraction of those are the near-Earth asteroids, the ones that are crossing the Earth's orbit at some point in their journey around the sun. And Vera Rubin, in 10 hours of observing, found 2,000 previously unknown asteroids. And so, in other words, the expectation is that it is going to find 10 times the number of asteroids that the rest of the astronomical community finds, combined. That it is going to find 5 million asteroids over the course of its 10-year mission.
Sort of. They anticipate they will bring the total number of known asteroids to
another
5 million.
4, right. So another 4 million.
Yeah.
Sorry. Yeah. So that was the kind of thing that I was really hoping that they would talk more about, and then talk about that in terms of supernova, and talk about that in terms of variable stars. They hinted at it, but I think they just wanted to show people like really beautiful pictures and get across the sense of the magnitude of the camera, which is that it is a really big camera.
Yes. Yeah, it's ludicrous. This camera has a 10 square degree field of view, and it has 3,200 megapixels per image.
Yeah.
They're planning to take 30-second exposures that are still getting down to like 20th magnitude, which is insane.
Yeah.
And they're planning to do about 1,000 science images per night, 2 million images per year. They are imaging the entire sky every 3 to 4 nights.
Yep.
It is ludicrous.
Yeah, and I think the part that I hope people will walk away with is that it's going to be observed, as you said, every couple of nights. It's going to do this full pan of the entire sky, and then it's going to come back and it's going to do it again, and then it's going to do it again, and it's going to do it again, and it is going to, over the course of its 10 years of operation, it's going to take a picture of each spot in the sky 800 times. And so if you want to sort of understand the significance of this, imagine if you could run a video of the night sky where you took a frame that happened every 3 nights for 10 years. And then you notice something that happened in the sky 4 years ago.
Yeah.
And then you go, oh, wait, does anybody have, we noticed there's a new supernova remnant over here. Does anybody have archival footage of when that supernova went off? Oh yeah, it's in Vera Rubin. Let's go back to that date, and you can look back in time and watch that you could make a video where you just put up one frame per, 30 frames a second of the sky and run it for many seconds. You would watch all of the asteroids zipping past, all of the Kuiper Belt objects drifting through the field of view, all of the, the planet nines, all of the supernova going off, all of the variable stars that are across that entire field of view, stars disappearing because they've just directly collapsed into supernovae.
Yeah.
Supermassive black holes coming online because they're now feasting on new material that's falling in. Previously active supermassive black holes shutting down because there's no more food to eat. So it's just this way to see the universe in this dynamic way that nobody has ever been able to do. Every single survey that we've ever had up until this point has been like a one-time survey. You just take one picture of every spot in the sky and you call it a day. And that's been a game changer for astronomy. So now you're not taking one, you're taking 800 of every single spot in the sky at a level of depth that rivals the capability of the largest telescopes in the world. So it's all bonkers. I hate that we're having to use these superlatives. Like, it's crazy. It's bonkers. It's madness.
Yeah.
And yet it really is. And I think people aren't going to really appreciate how much this is going to change astronomy until we're a couple of years into this. And you're like, oh yeah, another thing that people found on Vera Rubin.
I think it's going to be more like 6 months to a year when we start seeing it. This is one of the large telescopes in the world. It's 8.4 meters. There are a bunch of telescopes in the 8 to 9 meter class. But what makes this one so weird looking and awesome is, any of you amateur astronomers out there know that the focal ratio in a lot of ways tells you how quickly you can take an image. So if you have a super small focal ratio, you can take wide field, super fast images, but you usually have a trade-off that you end up with really bad resolution when you do that. Well, the Rubin Observatory's Summon the A telescope has a focal ratio of f1.234.
Right.
It is the stubbiest little telescope I have ever seen. And because of how it's built, they have 0.2 arc seconds per pixel. So they are super saturating their pixels. It's insane. They have 10 micron pixels on their CCDs, and they have 189 4K by 4K science CCD chips. These are not CMOS, these are CCD chips. They were saying in the live stream that the camera is the size of a car but weighs a whole lot more.
Right. Because
It's
it's like solid electronics. It
yeah.
doesn't have the air inside where
No.
the people might go.
No, it's
Yeah.
it's wild just how different this observatory is. And the reason it was built this way was once upon a time it was funded through a combination of private funding, NASA funding, National Science Foundation funding, and Department of Energy. Today, it's private funding, DOE, and NSF. I'm not sure what happened to the NASA funding. I no longer question these things. But that combination of funding was in part to do the things that we expect all new telescopes to do, looking at dark energy, looking at dark matter. But then it was also trying to protect our planet because the total fraction of asteroids known we knew wasn't that great. The number of potentially hazardous to our ability to continue as a civilization number of asteroids known wasn't that great. And with its high sensitivity, with its large field of view, with its constantly repeating the sky, it's going to find everything moving.
Yeah.
And help protect us.
All right, we're going to talk about this some more, but it's time for another break. And we're back. So I want to give like some other just interesting numbers. For example, we currently know of about, say, 2,000 to 3,000 type 1A supernovae. And we've been finding these for 30, 40 years. These are the supernovae that have created the discovery of dark energy. Nobel Prizes all around. And each one of these type 1A supernovae is so precious. Because there's just so few of them that have ever been found. They're a very rare event. Well, Vera Rubin is expected to find 1 million of them.
4 million supernovae in general they expect to find.
Yeah, and 1 million, and with 1 million type 1A supernovae. You've got all of these variable stars that are going, they're changing in brightness, and that there are some really rare ones like RR and even like double RR stars that are really important to astronomers as sort of standard candles, as well as ways to measure the expansion of the universe and so on. Again, we will know of so many more of them because it's not just seeing things that happen on a regular basis. Those exist. Like there's the Zwicky Transient Facility, which is a telescope that is scanning the sky every couple of nights. It's found tons of asteroids and so on. But this is both an incredibly powerful telescope. It could stand up and take as good of a picture as any telescope that's out there on the planet. And yet it can do it in 15 seconds and move on, right? Like done, next, done, right? That's where this thing just comes into, pardon the pun, focus, is that it's not just about the power of this telescope. It is about the speed and how much of the sky it's going to be able to keep track of.
And to give you some ideas of the science, with RR stars, they are horizontal branch stars, which means all of them are more or less the same actual luminosity. And when we look at them, we can identify them by how their light changes over time in very distinctive ways. And if we can measure how bright they appear and we know how luminous they are, we know where they are. And because our Alaris are low metallicity stars, we're going to be able to use them to map out the distribution of field stars in the halo. Right now, we're doing great work with dwarf spheroidal galaxies, dwarf elliptical galaxies, globular clusters, all of these groups of stars that exist in the halo. This is going to allow us to see these fainter objects, they're fainter than Cepheids, these lower metallicity objects, and actually see the true extent of our galaxy in all directions that aren't blocked by dust and gas. And that in itself just has me super, super excited.
Now, Now, one of the things that I did find interesting with the presentation that they gave and the images that they showed, in many cases they were done with dozens, if not hundreds,
Yeah.
of exposures in the same area. And that's sort of like they were showing you what it might be like if you just compressed all those 800 images
Yeah.
into one shot, which is interesting. But then you sort of lose that time dimension when you're looking at all of that. You're
Yeah.
essentially using all the separate images to improve the data and remove the noise, which is great and important. But in addition to this sort of the general survey, this is the LSST,
Right. Large
legacy
legacy
space.
survey of space and time.
Right. They're going to do some special operations
Yeah.
where they're going to look at some specific areas and they're going to observe them very intensely on a very rapid cadence. And so we're also going to see stuff where like maybe there's some place where we're, trying to see how variable stars are changing, or a place where we know there's a lot of supernovae going off and get a much better sense as well. So there's not, and I think sort of the images that they shared are sort of more in line with that philosophy that you're keeping the telescope locked on one area and going click, 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 and taking a bunch of pictures. So for places that are, in addition to just this, the full survey of the sky, we're going to get some regions, and that will almost be the equivalent of Vera Rubin's Hubble Deep Field.
Yes.
Right? That it's going to take a place that is very dynamic, where maybe things are changing down to the second or the minute, and see what you can capture if you just take picture after picture after picture of that same area. So there's a lot of other interesting science that's going to come out of this as well than all of the stuff that we've been talking about.
And they really designed this around four, they call them pillars of science. And this is where, so like I alluded to, they're doing that standard question of where is all of the dark matter and how is dark energy changing the shape of space over time? And so with their image after image, they're starting out hitting low 20s in magnitude, which is ludicrous to think about.
Yeah.
And then they're
just for comparison, the European Southern Observatory, I think they're
Yeah.
at 27. Hubble can do 32. 30? Yeah. Anyway,
but
so
those are with like significant numbers of
hours, days.
They're in 30 seconds
Yeah.
hitting in R. This is Sloan R. They're hitting 24.7 magnitude in a single exposure.
Wow.
Yeah, so it's ludicrous. So they're able to map out galaxies at a whole variety of different distances. And by looking at what was the universe doing in the great distance, what was it doing in the middle distance, what is it doing nearby, what are all these galaxies doing, how is the shape and structure of the large-scale structure of the universe changing, that can tell us how dark energy has changed over time. So this is working in lockstep with the Euclid mission, with the hopefully to be completed Roman Observatory. All these missions and this program are working together to solve dark matter, dark energy. But in addition to that, it's literally inventorying our solar system. It is finding the near-Earth asteroids we need to watch out for. It is looking to figure out just how often do alien asteroids plunge through our solar system. If there's a planet 9 through N out in the outskirts of our solar system, it will find it or them.
Yeah. It's expected to find dozens of interstellar objects every year. We know of Oumuamua and Borisov, and that's it.
Yeah.
It's going to find dozens, if not hundreds, of these every year.
If we have the models correct, and that's the thing. This is going to tell us if we have our models correct for things we don't fully understand. And so we're getting discrete data on where are the centaurs, how many of them are there, what, all these different things. It just blows my mind. We're literally going to have more data on what's going on in our solar system than you could monitor on a computer monitor.
All right, we got to take another break.
Okay.
And we're back. All right, so where do things go from here? So we've seen first light, but they're still in the commissioning phase.
Yeah.
The actual the survey has not begun yet. So
Correct.
what is going to be happening next?
So they're continuing to figure out their entire pipeline process and commission the telescope. So what they're
Right.
doing is they're figuring out everything from how does the system flex depending on where it's pointed on the sky. This is something every telescope does. They're physical objects on a world with gravity, they flex. So it's figuring that out. It's figuring out how focus changes over time. It's figuring out what are the details for getting the data reduction pipeline working. They're pulling down terabytes per night.
Yeah, they're going to pull 500,000 terabytes, and they're transferring this all in real time from the telescope to the servers in the US.
Yeah.
So they're not sort of storing it locally on the telescope. They're moving it right away and then processing it in real time to give astronomers alerts.
Yeah.
Supernova, we just found a supernova here. We just saw an asteroid over there. There's Planet 9 over here. And then if people want, they can dig through the data for their own specific things. Show me every image that was taken in this part of the sky over the last 10 years, and you can get them all.
And one of the things that truly amazed me is, so with 20 terabytes per night, they were originally thinking, shit, we're not going to be able to keep all the data. We're going to have to throw stuff out. And that's one of those things that will make any astronomer curse. And we thought we were only going to be able to keep data tables because there was just no way all the raw data could be stored. But in the 20 years it's taken them to get this telescope built, commissioned, and out the door, there were delays with the pandemic, there were delays with social unrest. Working with Cisco Systems, taking advantage of new infrastructure built into that part of Chile. This is on the Serra Fashion Mountain, which the subtitles literally wrote Sarah Fashion during the presser. It was hilarious. They're transmitting all the data to SLAC here in the United States, the linear accelerator out at Stanford. They're also transferring information to Europe. There will be multiple repositories. And with their 11 data releases, there's going to be 15 petabytes of data.
Wow.
Yeah. So
crazy.
This is completely new layers of data management. There will be 6 million orbits of solar system bodies that they figure out through this survey.
Yeah. So I think, hopefully this gives you all a good sense of expectation, what to be looking out for. It's not about the pretty pictures. Yeah. It's about the events unfolding in the sky that we will now be able to capture. And I think that the thing that I'm most excited about is the thing that I don't know about yet.
Yeah.
Now that we're watching everything, I always describe it as we're finally going to see the things that the universe was doing when we weren't looking. Yeah. Now we're looking, and it's going to be entirely new phenomena that will be discovered through this process where someone goes, hey, I just saw a thing and I don't know what it is. Have we ever seen any of these before? Oh yeah, here's 42 of them in the Vera Rubin data. Let's figure out what they are. And we're moving to this sort of additional understanding. But hopefully this will prepare everybody for what comes next, because it is going to be a busy decade.
It really is. And what's exciting is we have other giant telescopes coming online that will be able to do follow-up observations. We have the Square Kilometer coming in future years. The amount of infrastructure scattered around our planet allowing us to understand our universe is unlike anything we thought we would have when you and I were young. And here's to hoping that there will be plenty of scientists to get to explore it.
Wonderful. Thank you, Pamela.
And thank you, Fraser. And thank you so much to everyone out there funding everything we do. This week, I would like to take a moment to thank Adam Anise Brown, Alexis, Andy Moore, and Astro Bob, Bart Flaherty, Benjamin Mueller, Bresnik, Brian Kilby, Kemi Rassian, Conrad Haling, Danny McGlitchy, David Green, Disastrina, Dwight Ilk, Evil Melky, Flower Guy, G. Caleb Saxton, Glenn Phelps, Greg Davis, Helga Bjorkog, Janelle, Jeanette Wink, Jim McGeehan, J.O., John Herman, Jordan Turner, Kate Sandretto, Kenneth Ryan, Christian Magerholt, Lee Harborn, Marco Iorasi, Masa Herleu, Maxim Levitt, Michael Purcell, Mike Dog, Nick Boyd, Pauline Middlelink, Planetar, RJ Basque, Robert Plasma, Sergio Sansevero, Scone, Semyon Torfason, Slug, Stephen Miller, The Big Squish Squash, Thomas Gazetta, Travis C. Porco, Wanderer M101, Zero Chill, Alan Gross, Andrew Allen. I started reading next week's names. Thank you all so very much. We have one more episode this season. It's not going to be a happy one.
Yeah. Thanks, everyone. We'll see you next week.
Bye-bye. And then they saved. And I'm going to remember to put it in the correct directory. All right.
Okay, I will do the same.
And I just want to apologize for what happened last week. I tried my best, folks. I tried my best. I have a 2018 laptop that generally exists for Google Docs, things like that. And while we were recording last week from one of my friends' houses where they had internet, unlike my house, it was dying. It was pulling so much power trying to record, trying to stream. It was plugged in and still running down its battery, and that was not. Yeah, it was.
That's amazing.
It was bad. Yeah, as soon as we were done with the episode, I looked and it was like 8% battery.
Yeah.
Yeah.
Plugged in. Yeah. Yeah. Might be time to put that one out into the pasture.
I think I need to just not try and record on the go on it.
Yes.
I have this lovely device. I just can't stream from it. So it may be that in the future, if we have to do something like that, I have Ustream. And then I
Right.
Yeah.
You show up.
Yeah.
Yeah. Or take your Mac Mini. It's pretty portable.
That's true. I just then would need to purchase a screen.
Just plug it into someone else's screen.
That's true.
Or a TV or whatever.
Yeah.
I do that sometimes. I'll take my computer and plug it into the TV, and then when we're on the road, we'll watch the TV through the computer. Yeah.
Very cool.
Because every TV has an HDMI port.
Yeah.
So as long as you get your access to the HDMI port, you're all right. Okay, let's move through the questions. Chris Casper asks, are amateur citizen science groups creating guides for the public use of Vera Rubin data? Not yet.
Not yet. I know there will be citizen science projects that are built around LSST data. Ironically, I was part of helping get LSST and Zooniverse engaged working together 10 million years ago. and so those will all be over on Zooniverse. But there's also plans to do alerts so that when there are objects at brightnesses achievable by amateur telescopes, folks will be able to observe those objects.
So they have a thing they're called data brokers. And so what they're doing is they are they've got a bunch of partners, universities, space agencies, various people around the world, where they are sort of passing this high-level data through them initially, and they're going to help create visualizations and ways to be able to access the data and also be able to see it in real time.
Right.
I actually talked to the people at Vera Rubin about this, that, what are some kind of cool things that they could do to show people. Like, for example, you can go and see what Hubble and James Webb are looking at right now. There's you can't actually look through the eyepiece, but you can at least know where they're pointing right now. And there are similar types of stuff that will eventually be in the works. And the nice thing is that pretty much, everything that's coming out of Vera Rubin is just going to be freely available. And so people will come up with all kinds of really interesting ways to visualize that data.
Yeah. It's a good time to be a data scientist.
Arjun asks, is 10 years enough time for us to notice our own movement through space?
Uh, sort of. I mean,
Oh, yeah.
we're not going to be able to see how we move relative to the center of the galaxy, but 10 years is long enough to be able to see a lot of stars moving in orbits relative to ours.
Yeah. I mean, that's what Gaia was for.
Yeah, yeah. Gaia definitely was designed around that idea.
Yeah. Mike W. asks, are astronomers going to have to develop new data processing pipelines to handle all of this crazy data?
They've been developing those for the past decade. There's been a lot of work funded by the National Science Foundation to using often the dark energy survey data for beta testing to develop machine learning algorithms where their first pass through the data uses the machine learning algorithms to identify this is a galaxy, this is a nebula, this is a we don't know, spit it out to a human being, please. And one of the useful things about astronomy is you have light or not light. And so you can have your machine learning algorithms chop out the brightness parts, try and identify those. And we are to the stage in machine learning training where we can apply percentages. This is 80% likelihood a spiral galaxy. This is 20% likelihood a elliptical galaxy. And based on those likelihoods, we can start to say what human beings need to review and what they don't. And this is going to allow us to go, oh, we have 30 similar looking things that the software didn't know what it was. Lets a human being figure out, oh, that's an entirely new kind of galaxy merger we've never seen before, and then train the algorithm. And so over time, we're just going to be increasing how the software can use its virtual eyes to identify things for us, allowing us to focus on just doing the science.
Arjun asks, over the years, will the image we have of the universe get clearer and clearer, sort of like when you stack an image?
Yes. So to give you the numbers, hold on, I'm scrolling through my chart. So going back to that R magnitude image, they're starting out with a 30-second exposure. We'll get them to 24.7 magnitude, they estimate. And remember, this is a logarithmic system. After 10 years stacking those 800 images, eliminating, this is the ultimate arch nemesis of low Earth orbit satellites.
Right, removing all the satellite trails.
Yeah. So they estimate they're going to be able to see down to 27.5 magnitude.
Yeah.
So that's
closing in. I mean, that's what you get with the big telescopes. That's closing in on what you get with Hubble when you're attempting to observe one specific spot, except you're doing it for the entire sky. And so that's what those data releases are going to be, is they're going to be the stack of the data at gathered so far. And that it will, the image will get better and better and better over time as they do more data, less noise in each one of these stacks.
Yeah.
People are noting that they need one in the northern hemisphere.
So yes, not arguing with you. This one goes from roughly off my head 70 degrees south to 12 or 15 degrees north. So yes, they need one in the northern hemisphere, but they are getting the equatorial regions of the sky quite nicely.
Yeah.
They have a really good region they're able to see, and they'll be able to get the ecliptic quite nicely.
Yeah. And like I think if this is as successful as people are expecting, then you could see one happening in the northern hemisphere, learning from the lessons. Like as you said, the development of this has been 20 years in the making. The telescope, I think they ground the telescope in 2009.
They were working on it. I have this mirror was originally broken memory.
I don't recall that. but
there was something that broke while they were building it. Here, I found a story. This is from 2014. It's not giving me the details. There was one AAS where they were giving away pieces of broken mirror.
Oh, right. I remember that. Yeah.
And so this was early on.
Like chunks of glass because they hadn't mirrored it yet. Yeah.
Yeah.
Yeah. One thing that's really interesting is the mirroring facility is there on the mountain.
Yes.
So they can sort of whenever they, because it's going to collect dust and it's going to get little bits and pits and it's just going to get less optically perfect over time. And then they can go pull it out, clean it off, resurface it, put it back in without having to like take it all the way back down the mountain the way they brought it up in the first place, which I think is quite funny.
This is the largest solid, well, I mean, it has a hole in the center. No, actually this one doesn't. They don't have a Coude focus. This is the largest, or rather a Cassegrain focus. This is the largest single solid-faced mirror out there. They're using a prime focus camera, which is why I had to correct myself. So the light comes down, it hits a mirror that is complete everywhere, just like you have with your Newtonian telescopes if you have a Dob. It then bounces up and it goes into the camera that is mounted at the top of the telescope. It's amazing. They do have a second. I need to look up how the optics on this works.
Yeah, so it's the
3 meter secondary.
So the way it works is that the primary is also the tertiary mirror.
Okay.
Right? So the light comes in, bounces off the secondary mirror. I'm trying to think.
Okay, clearly this is something we didn't either of us prepare.
Yeah. Right, but or am I thinking of the Daniel Cain way? No. The primary mirror is also the tertiary mirror.
And it does have a small hole in the center.
And then it has a secondary mirror.
Yes.
That's above. So it goes, the light comes in, down, bounces off, bounces again, and then goes up to the calendar. Yeah. So it bounces thrice.
There is a good diagram of this on Wikipedia. This is a very different design. I wonder why it has the hole in the center.
In the center of which?
Of the primary.
Oh.
I don't know.
Maura Labringi asks, has the project been funded to the full 10 years, including the cost of the data centers and bandwidth to share the data? Yeah, nothing is funded into the future.
Yeah, it's bleak right now, folks. But like I said, this telescope at least has mixed funding model. So two different government agencies in the U.S. It has funding from Europe. It has private donors. This is why it's the Simonier telescope in the Vera Rubin Observatory. It was a husband and wife couple that donated a huge amount of money towards that telescope. The naming of it was announced back in 2018. Having a mixed funding model is the only way anyone is going to move forward. This is why Patreon is so important to me right now.
Yeah.
We're going to go into this more next week, but we're looking at a minimum 50% reduction in grant funding, and it will probably be significantly higher than that. And most people don't have podcasts that pay their bills. And if I didn't have...
Do podcasts pay bills?
Escape Velocity Space News is doing okay enough.
Oh, good.
And this show is keeping Richard and Aviva and Allie funded. And yeah, so... yeah.
I don't see any more questions. Do you have any questions over on Twitch?
I'm seeing that we're going to need a bigger moon. That's no moon. That's the memory storage for the Vera Rubin. I'm loving the sarcasm. I live for sarcasm. Let's let's see what else. No, that they're just happy and chatty and sarcastic.
Good.
I love our Twitch audience.
All right. Well, let's wrap things up because
Okay.
we're on a non-standard day,
Yeah.
and I got to roll. So,
Okay.
thank you, Pamela, for taking the time to hang out with us today, and hopefully we will. This is just the beginning.
Yeah.
I think where everybody else is going to be like, ooh, new telescope. Moving on. In Middle East
No.
news, no, we're just going to be here nonstop, gushing about this telescope for the next 10 years. So just watch. I'll bet you we'll do at least an episode a year talking about Vera Rubin stuff. At least.
Yeah. I think that's probably an understatement, and that's okay.
Yeah, totally.
So yeah, wherever you are in the world, have a wonderful morning, evening, or afternoon, and we will see you on the other side. Bye,
All right.
everyone.
Thanks, everyone. See you later.